Alright folks, so in this video what I wanted to talk about is how you can build a multimodal RAG using ColPali. So this paper was introduced around 7th October 2024, which means that this is a very recent paper where they have kind of talked about how we can do efficient document retrieval with vision language models, right? So at first what we will do is we will try to understand how the ColPali works, and then in the end we will build a fully functional RAG pipeline using ColPali, right? So without further delay, let's get started. Let's first talk about what is a typical RAG system works in case of a complex document. Now that complex document can contain text, but it will not only contain only the text, it can contain a image, and also it can contain a table, right? So generally we call those documents as a complex document where we have a combination of image, table, text, right? So to kind of create the embeddings on top of these documents, what people generally do is they pass these documents through OCR technique, where we kind of do a layout detection, and using that layout detection, it will kind of detect where the images are present in the document. Then it will create a caption out of that image, so that that is kind of a textual representation of that image. And similarly, it will create the document chunks using the text part of the document, and using all of this, the captioning, the chunks, and the tables, it will create the chunk embeddings, and then that will be pushed to the vector DB. And once the user comes with a question, then we try to find out the similar embeddings or the chunk embeddings through the user question, and that we kind of return as the most relevant document to the question. So you can understand that this process is a bit complex, where we need a layout detection algorithm, and also as we are compressing the images with caption, so we are losing out the valuable informations that are present inside the image, right? So we are trying to solve this problem using the concept of ColPali. Now let's see how this is done using ColPali. So you can treat this as we will get the document, and we will kind of create a document screenshot, and on top of those screenshot we will create a patch image embeddings, right? So you can see in this document we divided the document screenshot into 4 sections, and in those 4 sections we are trying to create image patch embeddings. So then we pass those image patch embeddings through a vision LLM. At first it will go through a vision encoder, then it will go through a projection layer, and then again it will go through a LLM, which will create the corresponding embeddings for each of these patches. So you can see these are the embeddings for the 4 patches which is present here, right? So once that is done, then the user will come up with a query. Then what we will do is we will create a late interactions between this patch embeddings with the token embeddings of the query, and then we will kind of create a maximum score for this each of these pages, right? And then based on that maximum score, we will get the most relevant pages inside the document, right? Now if you are not getting familiarized with this concept of maxim, so I have discussed in my last video that how the Colbert works. So using that, you will get to know how the maxim works and how this late interaction works in case of like multi-vector representation, right? Now let's go through how the inner workings are for ColPali. So if you have seen my recent content in this channel, you will see that I have created a few of the recent videos which are related to either vision transformer, and also the last video which I created that talks about the Colbert, right? So those videos I created intentionally so that I can do a build up for this particular video. So if you haven't gone through those videos, I will request you to go through this vision encoder video, and also the Colbert video, which will take you through the key concepts which we will use in this video. right? So in the vision transformer, what we generally do is we try to solve the problem of how can we apply attention mechanism on top of images. To solve that, what we do is we create the patch embeddings on top of the image. So you can see the image got divided into patches. Then we kind of create a linear projection of those flattened patches, and then we kind of add the positional embeddings to the patch embeddings, and then we pass it through a regular transformer encoder layer to get a embedding representation which uses the concept of transformer, right? Then in the last video I already talked about what this late interaction is with BERT. So here what we do is, instead of creating a single vector for a whole chunk, what we do is we create the embeddings at the token levels, and that we do not only for the query, we also do it for the document level token embeddings, right? And then what we do is we kind of calculate the maxim score by using this late interactions between the query token embeddings with the document token embeddings, right? And then we kind of get the maxim score for that particular query for a particular document, right? So in that way we can calculate the maxim score by using this late interactions between the query and available documents, and then we will select the most relevant documents which will give you the highest maxim score, right? In this ColPali video, what we will do is we will replace this document embeddings with patch embeddings on top of the screenshots what we have created earlier, right? So this will we will use the screenshot to create the patch embeddings, and then that we will pass here to create the late interactions between the query with the patch embeddings of the document screenshot. Let's talk about a bit more detail. So as I mentioned, like, we will create a document screenshot, then we will create the image patches on top of that screenshot, and once we get that, we will pass those image patches through a VLM or a language vision model, and we will get the patch token embeddings for each of these patches, right? So we will get the patch embeddings for each of these patches, and that will be represented here. So you can see this patch embeddings, you can treat it as token embeddings, and that will have a dimension of 128. Similarly, we will create the token embeddings for the query. So the query will be passed through LLM, which will create the word token embeddings, which will be again of the shape of 128, right? And then we will calculate the maxim score by interacting this patch token embeddings with the word token embeddings, right? So as we are interacting with a lot of token embeddings, so this approach we generally call as multi-vector late interactions, because instead of creating a single vector for each chunk or a patch, we are creating multiple token embeddings at the query level and also at the image level. And so in that way we will fetch the most relevant pages out of the document using this concept of late interactions, right? Now let's compare this with the traditional RAG what we have. So one of them, which I already talked at the starting of the video, that once we are creating captions on top of these images which are present in the document, that will in that process we will lose out a lot of crucial information, which will not happen in case of this ColPali, where we are creating the patch embeddings. We'll also simplify this embedding creation process on top of the document, right? Because we will take a screenshot, then we will create the patches, and then we will pass it through a VLM to create the embeddings, right? Which is not the case in case of this typical RAG system, where we need to go through this OCR, then layout detection, then we need to pass it through a text embedding model to get uh, the embeddings for each of these documents, right? So here also we can see that this takes much lesser time when we are embedding the documents. So you can see like it takes around 0.39 second per page, but for typical RAG, which involves OCR and layout detection, that will take around 7.22 seconds per page, right? But there is a trade-off also. So we will get a higher latency in case of when we are trying to do the similarity match. So in case of ColPali, it will take around 30 millisecond per query, and for typical RAG it will take around 22 millisecond per query. But again, we will gain in terms of performance if we use ColPali instead of a typical RAG system for the complex documents, right? Also, if you go through the paper which I have showed you, you can see that the ColPali is leading in terms of different benchmarks. So they have kind of created a new set of benchmarks to for this complex document types, and you can see the ColPali is beating hands down to all the other techniques which are described here, right? So the maximum score is related to ColPali only using the late interactions which we have discussed, right? In the coding part, what we will do is we will do a few steps approach where we kind of get the corresponding source document, then we kind of pass those documents through the ColPali embeddings, which will create the image patch embeddings on top of the complex document, and that we will store to the vector DB. And once a prompt comes, the prompt will go through the vector DB to fetch the documents pages which will have the maximum score highest with the query embeddings, and then retrieve the top page images using this vector DB. And then what we will do is we will pass the LLM text prompt along with this top page images, and that we will pass through a VLM to get the corresponding response, right? So we will pass the prompt to the vector DB, which will have the late interactions between the image patch embeddings with the query embeddings, and then we will retrieve the top pages, and then we will use VLM to pass the prompt along with the top page images so that we get a better text response using this VLM which I have talked about, right? So we will have a document indexing process, then we will do image retrieval, and in the end we will do a generation phase where we will leverage a VLM to generate the final response, right? Now let's jump into the coding part. So first of all, we will install this library, which is from the inventor of Ragatuli library, which we have also talked about in the last video. So once that installation is done, we will install this popular utils, which will help you to load the complex documents, which we can treat it as a image screenshot, right? So then we will import this ColPali embedding model. So you can see we are importing this RAG multimodal, and there we are mentioning that we will import this ColPali v 1.2 model, and we will create an instance of this model, right? So once that is done, then what we will do is we will import this paper which I have showed you at the starting, which is again a ColPali paper. So that we will import, and that we will download in the Google Colab environment. Then we will index that document with the help of this model.index process, where we need to pass the input path of that PDF, and then we will also need to mention what is the index name, right? At first it will load this documents, then it will take a kind of a screenshot on top of each of the pages, then it will create the image patches, and then using the ColPali embeddings it will create the image patch embeddings, which would be a size of 128, right? So once that is done, then we can start firing some queries. We will pass a query where I am writing a question like what is ColPali's evaluation baseline score on docq and infoq, and then that we will pass that query to this model to do a search, and we will try to retrieve the top two pages, right? So we'll get back the results. So in the results we can see we have the page number that is associated with that complex document, then we have the score which is associated to that particular page, and also we get a base 64 representation of that page, right? So which is kind of image for that particular page. So you can pass this base 64 representation of the page to a VLM to kind of pass the prompt and also the image to the VLM to generate the corresponding response using this. right? So you can see like the page 17 is actually where it's saying that it has found the maximum score. Now, if we go back to the document of this PDF, so you can see I am at the page 17, and here you can see like it has the corresponding table through which it will try to answer the question. So using the ColPali embedding, our model kind of find out the best page which can be used to answer that particular question. Right, so our model is kind of working, and using this page it will try to generate the response for that particular question. Right, so then what we will do is we will get the base 64 representation of the first page which is associated with the page number 17, and then what we will do is we will build a multimodal RAG. So the pipeline looks like this. So we will pass a query, so that query will be passed to the index which is a ColPali embedding index, and then we will retrieve the most relevant page using the ColPali embeddings late interactions at the multi-vector level. And then once we get that corresponding retrieve page, we will fetch the corresponding base 64 representation. So then what we will do is we will pass the prompt along with the base 64 to a VLM. So in this case we will leverage the llama 3.2 as a VLM, and then we will get the corresponding result, right? So this is the flow which I have mentioned here also. So what we will do is we will leverage together. Using that we will use the llama 3.2 90 billion vision language model. So you can see I am initializing the client here, and then I am passing the query which is here, and also I am passing the base 64 representation of this particular page which I have created here. So that I will pass here along with the prompt, and then we will hope that the VLM will generate a proper answer for this query using this base 64 retrieved page using ColPali, right? So then we can see like we have got a response that the baseline score for ColPali late interactions on the evaluation criteria like docq is 54.4, and also the infoq score is 81.8, right? So you can see this is where this it got picked up and it showed you the correct results, and this is the result verifications which I am showing you. So I took the screenshot of that 17th page, and using that 17th page it kind of calculated the particular values for this docq and infoq using a vision language model. So I doubt this is actually possible if you use a typical RAG system. So you can already see how we can leverage this ColPali embeddings with VLM to build a more sophisticated retrieval on top of very complex documents, right? So similarly, we can do another query, which is a bit complex query. So you can see we have this page. So in that page, we have the two scores, which are like BM25 and BGM3 for docq evaluation criteria. So the score is higher for BM25 using the library which is like unstructured text only, right? So for unstructured text only between BM25 and BGM3, which model performs better for docq evaluation baseline, right? So this is a very complex question where it needs to parse this table, and then it needs to compare the results of two criterias of like BM25 and BGM3, and then it needs to find out what is the best between these two, right? Now let's pass this to our model. So we will do this model dot search, and we will only retrieve k equals to 1. So we will only retrieve the highest similar page, and then we will get the corresponding base 64 representation of that page. And then what we will do is we will pass the query and also the corresponding base 64 representation of that page, and we will see how the response comes, right? So you can see the response is actually correct. So at first it gives you details like to determine which model performs for docq evaluation between BM25 and BGM3 for unstructured text only. We need to compare the scores for docq column. So it understands that there is a column where the docq values are present for this two criteria, and then it fetches those results like BM25 is 34.1 and also the BGEM3 is 28.4, and then it tries to compare the results between these two, and it gives you the answer that BM25 is better compared to a BG embedding model for this particular type of evaluation criteria. Right, this is a perfect example which I wanted to show you, which you can leverage ColPali embedding with VLM to get more optimized results on complex PDFs. Right, so with this I will end this video. I hope you got a detailed understanding using this video, and I have been publishing the last few videos just to explain this concept of multimodal RAG using late interactions with ColPali. With this, I will end this video. I'll see you in the next video. Thank you.